So what are the impacts of tilth and organics on conserving water? Well, they have many positive aspects on slowing and retaining water in the system. So they're a form of soft infrastructure or building of system capacity to capture and retain soil moisture. So surface organics play a critical role in slowing surface flows, intercepting runoff, and slowing direct evaporation from the soil surface. This allows for a greater fraction of that surface water to infiltrate and diffuse slowly into groundwater. And as organic matters decompose and contribute to soil organic matter, they really improve the soil water storage. So you're getting the benefit of greater interception, less loss, and improved storage through organics and soil tilth. Let's go through in detail just some of these mechanisms by which tilth and organics work on the water conservation. So water loss through evaporation is a function of the area that's exposed, the amount of bare soil, and the evaporation rate. Surface organics reduce those evaporative losses on two fronts. First, by reducing the area of exposed soil, and this be it from a mulch, crop residues, or perennial vegetation cover. They also cool the soil surface and elevate the humidity, and those both reduce the evaporation rate. So in this example, you've got straw mulch between crop rows and plastic mulch on the crop rows. So there's no penalty for mixing and matching, but the overall effect here is that by having the entire soil surface covered with either crops, mulches, or a barrier of some type, you're greatly reducing the area of the soil that's exposed and thereby reducing your evaporative losses. Surface organics will slow and intercept surface water flows, so that vegetation on the surface becomes a physical barrier and increased friction to water movement. The slower that water moves, the more likely it is to soak into the ground rather than to pass over quickly and go out as an outflow. Soil organics and tilth also improve the infiltration rate by increasing soil porosity directly and indirectly. So indirectly, as we discussed a little earlier, by breaking up the soil aggregates and creating pore space, and indirectly by becoming a substrate for soil organisms. So they're feeding soil organisms, which do a lot of the churning and mixing of soil and creating porosity in the soil as well. Surface organic matter will decrease soil crusting, which again is another form of bad soil surface aggregate, because it creates a cap on the surface of your soil and prevents water from moving down. And organics in that surface soil layer also act like a sponge, so they will actually wick water down into the soil profile rather than shedding or pushing water away. This table, which I pulled from the United Nations Food and Agriculture Organization, just shows the different levels of water infiltration into various types of soils. It's the rate in millimeters per hour. You can see with either a clay or a compacted soil, you have a very low rate of infiltration. So if your precipitation is exceeding 5 millimeters per hour, then anything in excess of that with a clay or a compacted soil is going to be lost through runoff. And as you have larger particled soils, moving up from clays, things with the silt component, to sand, that infiltration rate increases from 1 to greater than 30 millimeters per hour. Organics have the same infiltration rate as sand, the coarsest soil particle, but it has a distinct advantage in that with sands, there's that very high pass-through rate. So they allow water to penetrate very easily, but they don't retain that water. Organics have a high infiltration rate and also a high water retention rate. The best of both worlds. So how much can soil organics improve your water storage? As an example, I've pulled here research from Hudson, published in the Journal of Soil and Water Conservation. The absolute numbers here are not important, but we'll just look at the trends. So this bottom line on both graphs represents the permanent wilting point. That's the level of water where it's too low to support plant life. So the plants wilt permanently and die. The upper blue line represents field capacity, which means all the water storage is occupied in the soil. Any excess water beyond that doesn't provide any benefit to plant growth. And so between field capacity and the permanent wilting point, you have what's referred to as plant available water. And so in either a sand soil or silt loam soil, going up by just 0.3 of a percentage point of soil carbon from 1 to 4 grams per kilogram in the soil, you're seeing a doubling with both types of plant available water. So as a rule of thumb, the USDA suggests that for each percentage organic matter that you have in the soil, that can hold roughly 16.5 to 25,000 gallons of water per acre. So that's roughly the equivalent of 1/6 of an acre foot. I put the acre foot reference in there as a common point for just to give you a frame of reference. In the central interior, and again as a rule of thumb, you would need roughly 1 acre foot of soil water per year to produce a good forage crop. So if you had 3% organic matter in your soil, you have roughly half of the soil moisture already buffered in the soil after snowmelt. So without any additional precipitation or irrigation endpoints, you're already starting from a standpoint of having half of your soil crop water needs buffered into the soil.